This video is for Physics of the Universe, Unit 1.2, Newton's Laws. Today's essential question is, what causes objects to start, stay, and stop moving? Hello, baby birds! Today we are diving into Newton's first law of motion, and our goal is to understand the forces that affect whether something starts moving, keeps moving, or comes to a stop. To anchor our understanding, imagine this scenario. A rocket is launched into space. It uses a booster to escape Earth's gravity. But once the booster detaches and falls away, something interesting happens. The spacecraft continues to move forward, smoothly and silently through space. No engines are running at this point. No fuel is being used. Yet, that spaceship does not slow down. It just keeps going. Why is this the case? That is the mystery we are going to try to solve today. To help us grasp it on Earth, we'll also look at a hockey puck gliding across smooth ice. Just another example of motion in a low friction environment. Let's zoom in on that spacecraft. The booster detaches. No more propulsion then. Yet, the spacecraft moves forward at a constant speed, meaning it doesn't slow down, turn, or stop. And it doesn't need any fuel to keep going. At first, this seems strange. Isn't motion supposed to require a force to keep it going? That is what a lot of people think. But that idea turns out to be a misconception. Here is that common misunderstanding. Many people believe that objects need a continuous force to keep moving. They assume that once the force stops, the motion stops also. But that's not true. What actually stops objects isn't the lack of a force pushing them forward, it's the presence of a force pushing back. On Earth, that's usually friction or air resistance. When a spacecraft is in deep space, there's practically nothing pushing back. No air, no friction. That's why it coasts without slowing down. And the same with a hockey puck on smooth ice. It glides for a long time because there's very little friction to stop it. To really understand motion, let's go back to the 1600s. Galileo Galilei, one of the early pioneers of physics, conducted experiments using inclined planes. He rode balls down ramps and then up other ramps. What he noticed was that the balls would roll up almost to the same height they started from. When he used smoother surfaces, they got even closer to that same height. On shallower ramps, they rolled farther before stopping. Why? This is because friction was reduced. Galileo was onto something. He realized that it wasn't a lack of pushing force that caused the things to stop. It was this thing we now call friction. Galileo took his experiment a step further in his mind. He asked himself, what if there were no friction at all? To do this, he imagined a ball rolling down a perfectly smooth surface. With nothing to slow it down, the ball would just keep rolling forever in a straight line at a constant speed. That idea, that thought experiment, became the foundation for what we now call inertia, which is the tendency of objects to keep doing what they're doing unless something interferes. So, when the rocket booster detaches and the spacecraft is left drifting through space, it's doing exactly what Galileo imagined. It keeps moving because nothing is stopping it. Now we fast forward to Isaac Newton, who took Galileo's ideas and developed 3 laws of motion. The first of these, often called the law of inertia, states, an object will remain at rest or continue moving in a straight line with constant speed unless acted on by an unbalanced force. This means that if no net force acts on an object, it keeps doing exactly what it's doing. If it's at rest, it stays still. If it's moving, it keeps moving in a straight line at the same speed. That's why the spacecraft we mentioned doesn't need any more fuel to keep moving. That's why the hockey puck keeps gliding until friction eventually slows it down. So let's break down what we mean by forces. A force is simply a push or a pull. Forces have both magnitude, which means how strong they are, and direction, meaning which way they're operating. When all the forces acting on an object cancel each other out, we say that they are balanced. The object either stays still or moves at a constant speed in a straight line. If the forces are unbalanced, the object will accelerate, meaning it will either speed up, slow down, or change direction. And yes, in physics, all three of those options are considered acceleration. Back in space, there are very, very few forces acting on the spacecraft, so its motion stays constant. So let's look at a couple of everyday examples. First, think about a book resting on a table. You know that gravity pulls it down. But did you know that the table is also pushing it up? These are balanced forces, so the book doesn't move. Secondly, let's push the book. Friction pushes back. If your push on the book is stronger than friction, the book moves. That's what we call an unbalanced force. The spacecraft that we keep on referring to is like that book, but with almost no friction to push back. That's why it keeps moving after the rocket booster falls away. This is inertia in action. Once in motion, the spacecraft just keeps going. No engines needed. It only uses fuel to change direction or speed, not to maintain its motion. The same applies with the hockey puck. It slides on the ice with very little resistance. It slows eventually, but only because of a small frictional force. In deep space, that friction is virtually zero. That's what makes space such a perfect environment to observe Newton's first law. So let's connect these ideas to sports. For example, in football, the more massive a player is, the harder it is to stop them. That is inertia. A larger mass means more resistance to change. In soccer, a ball keeps moving after it's kicked, until friction from the grass and air resistance slows it down. In billiards, when the cue ball hits another ball, it transfers force. The cue ball often stops because it has passed on its energy, which is another example of how force changes motion. And again, think about that hockey puck. Once hit, it glides until it hits another player or the boards. Let's do a brief calculation to apply what we've learned. A car is moving at a constant speed of 25 meters per second. 25 meters per second. The engine applies a forward force of 2,250 newtons. What's the force of friction? So, step one. Constant speed means no change in motion. Secondly, because of this fact, the forces must be balanced. With that in mind, that means that the force of friction must be equal to the engine force. Therefore, without doing any calculations, we can know that the force is 2,250 newtons, but in the opposite direction of the engine. So to wrap up, Newton's first law tells us that motion continues unless something interferes. The rocket continues moving after booster separation because there's no force to stop it. The hockey puck glides across the ice because of minimal friction. Objects stay at rest unless they are acted upon by an outside force. Objects in motion stay in motion unless acted upon by an outside force. Only an unbalanced force can change this fact. So remember, it's not motion that needs to be explained, it's the change in motion that reveals the presence of forces. At this point, you should be able to generate a full and appropriate response to today's essential question. What causes objects to start, stay, and stop moving?